Hey everybody, Dave Lindbergh in Hong Kong with another episode of the THD Podcast. Today's guest, we'll have Audio Precision coming on, and they're going to talk to us about the benefits and differences between using soundcards and audio analyzers for your test and measurement applications. But we need to give some props to our sponsor, Alti, the Audio Loudspeaker Technology International, and Audio Precision is a member, so you can check out their website and find out about all the benefits of networking and getting them involved with Alti. And of course, don't forget to subscribe and like and share all that good stuff on the YouTube side of things to help out promote our podcast. So without delay, we have Simon Weston coming in from Sendai, Japan. How are you doing today, Simon?
Summer's here, Dave. It's the cherry blossom time of the year.
Oh yeah, I've been there in April before. It's beautiful, and I've been to Tokyo for the cherry blossom time of year. It only lasts a couple of weeks, right?
Exactly.
Right. Okay. And joining us, I believe from the Massachusetts area, is Dan Foley, the technical sales engineer for Audio Precision. Thanks for joining us today, Dan.
Yes, hello, and hello, Simon and Dave, and thank you for giving me the opportunity here to talk about what I think is an interesting topic of when does it make sense to be using a sound card versus an audio analyzer? So I guess at this stage here, if you want me to jump into things, I've got a presentation on this topic I presented back in 2019 at Infocom, and it was pretty well received by the folks there at Infocom. So I'll go through those slides, which talks about what's happening with sound cards and audio analyzers, and I got a bunch of measurement data to show exactly what's happening. And
awesome.
Then we could have a little chat about things. Okay, so
great.
I hit the share, and I hit this, and then I think we hit this button, and lo and behold, something should be starting, right? So that's coming up.
Yep.
Perfect. So you got the full screen here. As I mentioned, this was a presentation that I gave back in 2019. So it's as relevant in 2021 as it is just a couple of years back. And the title of it was they're just the ultimate fighting championships of sound cards versus audio analyzers. Not to say that necessarily one is strongly competing against another. But as I mentioned, there's oftentimes a lot of confusion as to where does it make sense to use one piece of technology over another. Just before I jump into this, though, AP, we've been around for a long time, but there might be some viewers out there that are not familiar. Who is Audio Precision? So the company actually started back in 1984. These are the four gentlemen, former engineers at Tektronix, that actually were involved with the first audio product that Tektronix developed and put to market back in the 70s. And then they saw an opportunity for expanding on this technology for audio tests, and voila, Audio Precision was born. So the company's got very, very strong roots within Tektronix world. In fact, the corporate headquarters is still in Beaverton, where Tektronix is. So with today, we're definitely known as the standard for audio tests. Our little AP bug, as we call it, for the logo. You'll often see that on data sheets from silicon manufacturers. And the thing is that we're dedicated to the audio test world. And then there's distributors all over the world, which you can find on the Audio Precision website, but we do have direct technical salespeople in the US and the UK. And as I said, there's distribution throughout the world. So anyone who is viewing this presentation, if you're not sure if there's someone you could talk to at AP to get more details, just simply go on the website, ap.com. And there's probably a very good chance that wherever you're at, there's someone that can help you out. So what are the things that are nice about sound cards? Well, first of all, they're everywhere. They both could work in Mac and the Windows world, and on a cost per channel basis, they're actually a really, really good deal. Sound cards have been around for a long time. Audio analyzers do predate them, but the sound cards that are out there, especially the higher end cards, oftentimes actually the same chipsets. Converters, the D to A to D chips used, especially in the higher end sound cards, are actually the same that are used in audio analyzers. However, how the designs go forward, these are some things I'm getting into, are fundamentally different, even though the actual converter technology might be 100% identical. So on the audio analyzer side, if you look at it just from a business standpoint, Soundcards you can get on Amazon, at least here in the States, you've got Guitar Center, Sweetwater, etc. With audio analyzers, typically you've got a specialized sales channel. And then depending upon the channel count, the very typical configuration is 2 channels out, 2 channels in. Why? Because we have 2 ears, and the audio industry grew up around stereo. It's really that. In today's world, sound cards, there's still stereo sound cards out there, but for many applications, especially for recording, people will get multi-channel cards. And one of the nice things with sound cards is on a standpoint of the impact to one's pocketbook, the cost per channel is much, much less than that of audio analyzers. So let's take a look at some of the typical specs of a sound card and see how that differs from an audio analyzer. So with sound cards, a typical input impedance is about 10 kilo ohms, although one of the sound cards that I'll show some measurements later on has actually got an input impedance of over a mega ohm. And the output impedance is typically 100 ohms or less. And the maximum input is 10 volts or less. And sound cards do not have auto ranging circuitry. So why am I bringing this stuff up? Now, in the world of electro-acoustic measurements, it's not that critical, because if you're going to get 10 volts out of a microphone you're using for measurement, you're probably measuring a nuclear bomb going off or something, because the voltage levels coming out of most measurement mics, when you get into the several volt range, the sound pressure levels are just totally insane. But when we're starting to talk about amplifiers and other electronic devices that can have some considerable higher voltage level outputs, then sound cards just might not cut it. Number one, you run the risk of blowing them up. And then there's other issues in there with measurement accuracy, as far as having an input impedance that is only 10 kilo ohms. Likewise, having only one selection of output impedance. And then auto ranging. This is something that is extremely important with audio analyzers. And I'm just bringing this up as a point because anyone out there that's in the market for an audio analyzer, this is something that's pretty critical to get, whether it's an AP product or anyone else's. Hopefully you want to be considering what we have to offer. But here's the reason behind auto ranging, is that any chip, especially on the A to D side, there's a finite amount of voltage, right? Well, you can go to 0 volts, but then you got noise floor issues. But there's a maximum voltage range that you can put into the chip before you basically have 0 dBFS, right? Full scale deflection. So what the auto ranging circuit does, and in the case of every AP analyzer, the analog signal hits the auto ranging circuit first. There's a comparator circuit. The comparator circuit says, okay, what voltage level are you? If it's a really low voltage level, it'll actually kick a little bit of gain in there, so that the signal levels are always, as much as possible, always within the sweet spot of that converter. In other words, trying to utilize as many bits of that A to D converter. And the same thing on the D to A side, but especially on the input side, the auto ranging is basically, regardless of voltage level, always trying to utilize as many bits of the converter as possible. So that's a key reason why auto ranging is extremely critical for measurements, in particular for any device that's going to have some higher voltage level outputs. So what's happening with an audio analyzer? So many pieces of test equipment will have a 1 mega ohm impedance. In the case of AP, we've got a 100 kilo ohm input impedance. In the case of balanced inputs, it's 200K. It's 100K from plus to ground, another 100K from minus to ground. Why did we choose 100K? Because I get this question asked quite often. Was a trade-off. Every engineering design is nothing that's going to be absolutely perfect. Engineers always make trade-offs. The trade-off here was that if you go with a higher input impedance, well, that's very nice, because you're going to have the input of the test equipment have that much less of an electrical loading effect on the device you're measuring. However, the noise floor goes up. So the 100K value was chosen as that trade-off between, giving up a little bit on the aspect of the front end loading the device under test, but it also means that there's much less noise of the resistance itself. And that's what I was mentioning in here about the higher noise. And then the other thing with most audio analyzers is you don't have one output impedance. You have several. So now you can match output impedances much more closely of the generator section to whatever sort of device that you're measuring. And then with, at least in the audio precision side of things, we've got some of our analyzers could go actually up to 230 volts peak. And as I mentioned before, the auto ranging is for all about optimizing, the number of bits used in the A to D converter. So when we talk about connectivity here, with an audio analyzer, you have the common connectors for any piece of test equipment. In the audio world, balanced is XLR. That's what we have on our instruments. There might be some people out there making audio analyzers with a 1/4-inch tip ring sleeve. I've not seen them, but it is going to be a balanced inputs as well as outputs, and BNC, and then of course on the digital side, your AES3 stuff. And then sampling rates can vary from extremely low to extremely high, and many sound cards can handle these sampling rates without any problem, and many sound cards are 24-bit as well. Actually, not sound cards as well as audio analyzers. I put 24 bits here in question mark. I'll get into that in a moment. So with sound cards, what you typically will not have is a BNC for any type of single-ended input. That's not that big of a deal because you can use some adapters, but you just need to be cognizant of that. I've never seen sound cards with BNCs out there because they're not a typical audio type of format. And as I said, sampling rates, this was a lot of the sound cards. In the olden days, it only went up to 48K. Now it's all very rare to find a sound card unless it's a very low end price-wise that maxes out a 48K sample rate. So why do I have 24 bits with 2 question marks in here? Well, here's the thing. Not all, let's say, sound cards or digitization devices are created equal. Without naming names, there have been many instances where I've gone to measure sound card devices where you look at the specs and they're using a 24-bit converter, and there's some specialized test signals that we have in the AP analyzer when we put a signal in, and find out that, that really is only 22 bits or 21 bits. So these are things in here that the spec sheets, they might be a 24-bit converter, but depending upon what's going on, it can actually be what's called the ENA, the number of effective number of bits. That's a critical spec to know about, and that may or may not be listed in sound card specs. So here's one of our analyzers. This is our let's say, entry-level analyzer, the 515, which is quite popular in the market for both electro-acoustic and especially electronics measurements. And this is the thing I want to point out, is that all of our analyzers, and this might also be the case for other manufacturers of dedicated audio analyzers, there's a grounding point on there. And man, the number of times that I've been in situations where engineers have been struggling because they have just ground loops, or they have these myriad of different grounding points with their test setup. And their data acquisition device, I mean, forget about it if it's just got 2 prongs. But even if it's got a grounded plug, it's like, what's going on with with the grounding in there? And ground loops can be pretty easy to detect, especially if your software's got FFT analysis, which the AP software does have that. You can see these giant spikes at 60 hertz or 50 hertz in any harmonics. But when it comes to just poor grounding, that could just cause an overall rise in noise floor as well, in addition to whatever might be happening with power supply or line frequency harmonics. So the ultimate fighting championship here, the measurements that I did that I'll present, I used the 515 analyzer and compared that against my quite old, like probably 10 plus years MAudio Fast Track. So I would not say that the MAudio Fast Track is of current technology, but it's pretty standard with what's out there. And then I do have measurements of a much more modern sound card interface that I have, an 8-channel interface, and you'll see that it's got actually some actually quite good performance, but it's still not quite that of an audio analyzer. So here's what the Fast Track Pro, in fact, some of you listening and watching this might even have this there, or at least used it at one time. So what I did for the measurements is that I was using the analog generator for the 515. I put plus 3 dBu into the interface, and then I use both sine and multitone. For those of you that might not be familiar with multitone excitation is exactly what the name says here: multiple simultaneous sine waves. So intermodulation distortion, 2 sine waves, think of that as the most simple multitone. So multitone is just some number 2 on up of simultaneous sine waves. Why did I use this? Mainly because of multitone excitation, 2 key factors, and I'm a big fan of multitone, is that number 1, the crest factor is not 3 dB. So music and speech are not 3 dB crest factor signals. So using sine waves, yes, it's easy to interpret distortion because it's harmonic and so on, but it's also a 3 dB crest factor, and hence a signal with higher, a deterministic signal with higher crest factor could actually generate some distortion characteristics that you will not necessarily see with a sine wave. And then I just captured all of these as wave files and then did some analysis. So you'll see all the measurement results in terms of dBFS. So just hooked everything into here. So analog out into the inputs on the Fast Track, and then just analyze the signals via the laptop. So here's the control software with the mode of what's called bench mode. So bench mode is an interactive mode. In the AP software, there's 2 user interfaces. There's bench mode, which, as the name implies, it's a much more interactive interface. So you've got panels where you've got a live oscilloscope, live FFT. The number of channels are based upon the number of channels of the analyzer that you're using. And then you have a whole range of different single value measurements, gain, THD, crest factor, RMS level, phase, frequency, a whole bunch of things in here. And then there's another mode called sequence mode, which is used for test automation. So here's how I did the measurements in here to go a little bit more with the user interface, is in this mode called file analysis. In here we can just choose wave files, so it's pretty cool that you can capture wave files with any device, as long as you have a wave file that can be fed into the AP software, and then run that to do the analysis. Now, to get analysis here, you either have to have either what we call our APX flex key as a dongle or an analyzer in here, but you can do analysis after the fact. And then the results are put into what we call a measurement window. So let's take a look at some of these test results in here. First, looking at self noise, industry standard test of THD plus noise at a 1 kilohertz frequency, and then looking at what's going on with multitone, where the total RMS level was right around plus 3 dBu. So with the self noise in here, usually, as I'm pointing out, it's typically shown as just an overall number. So I'm bringing this up to you because when you look at self noise specs, whether it be for a piece of test equipment, audio interface, any piece of gear you're looking at, make sure that the bandwidth is specified, because again, oftentimes you'll see some pretty attractive numbers, which are typically done in the audio bandwidth, because guess what? Humans hear from 20 to 20K. But if you want to do measurements and or recording at higher sample rates, 96 and even 192K, that noise floor number is not necessarily valid anymore, especially if they don't specify what the bandwidth is. So if you see some specs that are very attractive and you just think, oh, well, that should also translate out into a higher sample rate, don't necessarily go down that route. Now, one of the things that's critical in looking at noise, and I'm a huge believer in doing FFT analysis of these signals, is you get a tremendous amount of insight, even if that noise floor, and even with THD plus noise and other measurements, even if that number is like, wow, this is fantastically low, fantastic spec, the FFT is the truth teller. That's able to give you all the information as to what's going on to say, well, man, there's a lot of junk coming in from the power supply of this device. Or what the heck is going on in here? I'm seeing some garbage way up in higher frequency ranges, which could be related to some poor RF shielding. I mean, one of the pieces of test equipment we have at AP, we can actually measure with 24 bits of resolution out to 1 megahertz. And there's been many times where I do measurements out to megahertz, especially if it's just all analog stuff, and find out that, oh, look how nicely this is picking up all these lower band AM radio signals. And now that junk can beat down as noise into the higher end of the audible range. So FFT analysis is an absolute must, in my opinion, for ascertaining what's going on with your test equipment, not just for ascertaining what's happening with the measurement results. So I'm going to show you a way that when manufacturers present their noise data as an FFT, I'm going to show you a trick that they can use to deceive you. And deception is not nice. So these are, again, some tricks that I've learned over the years in here. Is that what's called the FFT bin. Now, so that's each line of the FFT. Think of them as filters. Well, those bins are based upon what the FFT buffer size is. So when someone says, oh, I have an FFT buffer of 4,096 points, you actually have 2,048 individual FFT bins or individual FFT filters. So that's a little easy thing to remember is when you're presented FFT data and you know what the buffer size is, divided in two, that's telling you then what the number of FFT lines or FFT bins are. So here's an example, and you can see this. I don't need to go to all the details in here, but it's just saying that at 48 kilohertz sample rate, we get a 4K FFT buffer. It happens to be a little bit under 100 milliseconds, so it means that each filter is a little bit less than 12 hertz wide. So you got massive amounts of, let's say, frequency resolution for higher frequency stuff. But if you want to find out what's going on with some detail in the low frequency side of things, especially down to 20 hertz, forget it. That FFT buffer is not going to do it for you because you just have filters that are way too wide. So here's some measurements that I made. So this was a 16K, 16,000 points. So now there's a little bit over 8,000 FFT lines, and you see with the math in here, they're about 3 hertz wide. So this was the noise energy of the sound card I was measuring, that MAudio file, or MAudio, and this is the wave file from that. So I just did an eyeball, the eyeball average. So this is an FFT of that noise spectrum. So it's basically about a minus 145 dBFS. Here's the key thing. Per bin. It is not the noise floor saying, oh, this is a noise floor of minus 145 dB. It looks really low because that's noise has been split up into 8,000 filters in here. So look at what I do. Oh, I'm in marketing. I want to make my noise floor be that much better. I'm just going to go and publish an FFT spec that's 96K and do an eyeball average. And wow, look at this. I now have minus 155 dB. Voila, I just got 10 dB more lower noise floor. No, you didn't do that. You're just playing some games in there. You just have a filter that's that much narrower. And therefore the noise energy in that filter has gone down. and I won't name names, but I have seen some very, well-respected test and measurement companies publishing their, say, self-noise of their input sections this way. And it's like, no, the way you should be publishing that is an overall number or, and I'll go in a moment, very specific ways of presenting FFT data. So here's what's going on as to where did this magic, 10 dB better performance come through. So with the first buffer that I used, it turned out to be 2.93, call it 3 hertz FFT wide. That was the buffer bandwidth that gave us an eyeball average of about minus 145 dB. So you see in here, we've got, let's say, a 3 hertz wide bin, right? So now I just simply crank up the FFT buffer size. Suddenly, I get to a bin. I basically crank it up by a factor of 6. Well, if the FFT buffer length increases by a factor of 6, the FFT bin size goes down by a factor of 6. So now we end up having, on a per bin basis, 10 dB lower noise. So this is something to be cognizant of. So how do you get around this? The way that this is done, and I got to say, this is the way that folks that, and I say folks, I mean companies that say primarily serve, acoustic and vibration marketplaces. It's like they're selling, high channel count data acquisition systems for aerospace and things like that. When you look at their specs, they typically present the FFT spectrum of their noise of their hardware either as amplitude spectral density or power spectral density. I have rarely seen this, like basically never, that I've seen this in spec sheets. I mean, it's rare to see an FFT of a noise spectrum of some piece of audio hardware. I mean, again, maybe up for a piece of test equipment, but I'm talking about sound card interfaces. I've rarely seen it, and let alone seeing it presented this way. So what this does with amplitude spectral density or power spectral density is it's basically, regardless of the actual size of the FFT bin, it normalizes it as if it was a 1 hertz wide FFT bin. So here's an example. You see it here. This purplish line is a 16K FFT, and then I go to 96K, and they're basically a little bit of the same. Now notice there's a tiny bit of a bump in here. Probably that's due to the fact that the raw spectrum of the 96Ks got a little bit more resolution, so it might be getting a little bit more energy that in a particular bin or so that wasn't there before. But at any rate, the bottom line is that you see that regardless of FFT bin size, it's normalizing everything as if the measurements were always done in a manner where the FFT bins are basically 1 hertz, regardless of what the absolute bin size is. So let's move on here and let's take a look at the next one in here. So I mentioned before about looking at FFTs, in this case, the power spectral density. So this is the blue data is the Audio Precision 515 analyzer, and then this is my MAudio. Even though the numbers are quite good, this is dBFS, so it's relative to full scale. So it's down better than minus 120. I mean, on an absolute basis, there's 16 dB higher noise. But this is where you can see the benefits of FFT analysis of noise. This is stuff related to line frequency interference, and it was not due to cabling or anything because I'm using all the balance stuff in. So in other words, if it was a cable problem, I would have seen that when I did some of these measurements with the AP, because in measuring the AP, I actually used the same cables for a physical loopback. So these sorts of things are telling me, okay, it could be a cable problem, but if you know that you got high integrity of the cables, in this case, this sound card interface, like saying, well, maybe there's some issues with the quality of solder connections with the connectors in there. Or maybe it's just not the greatest design. There's not the greatest amount or there's not as high a quality grounding as there should be with the power supply, or shielding from EMI and these other sorts of things. So this is where FFT analysis is invaluable, said to do like a deep dive into what's going on with what's really going on with these single value numbers of noise and even distortion for that matter. So looked at it on a total basis in here. Good sound card here for what's costing. Well, that MAudio, I think that's no longer being made, but it's probably not more than, I think when I bought it way back when, it was maybe even not even a couple of $100. That it's still a very good number, minus 130. But remember, this is not minus 130 dBV. This is not a voltage spec. This is relative to full scale. But you see that the AP now is still significantly better. So I'm bringing this up in the context of when you need to make measurements of especially low noise devices. And that does also mean for acoustic stuff, because on my experience in the biz in here, when it comes to high order harmonic distortion for acoustic devices, which will manifest itself, let's say, for speakers and rub and buzz, but even before a speaker may be buzzing or what have you. And there's many very well-respected electrical design engineers I know that put a lot of emphasis into seeing what's going on with high-order harmonic distortion for their electronics products, not just on the acoustic side. But these high-order harmonics, they could be minus 120 dB, minus 110. So these are things that your ears can pick up on. And I'm gonna just get out of this for a moment here, because I make a quick little shameless plug because I wrote about this. This was well, you can Google this, but I wrote this article back in 2016. Oh, it's in it was Audio Express. There we go, the March issue of Audio Express. I can hear it. Why can't I measure it? And this was specifically aimed at headphones, where I've had this many times. Engineers are going crazy saying, I can hear some little weird noises like, or whatever it might be, but just some noises that they're hearing. And this is in particular with not, I talk about headphones that have electronics in them, or the headphone amp or what have you. And then they go to measure it. They go, I hear something, I cannot measure it. So I'm just going to cut to the chase here. You can read the article, get into all the nitty gritty details. But here is, I won't mention the sound card. It's not the MAudio, but here's like the key takeaway in here. This, by the way, is a sound card that an audio test equipment manufacturer that they recommend for electroacoustic measurements. So blue curve is the noise floor with an electrical signal representative of 72 dB sound pressure level. So this signal, by the way, is 1 millivolt RMS based upon a microphone with 12.5 millivolts per Pascal. So what's so magical about this particular microphone sensitivity? That's the common microphone sensitivity in the microphones used in the ear couplers for headphone test fixtures. So what you're seeing in here is, here's the threshold of hearing. So it's actually below the noise floor of this particular sound card. So one could be hearing this stuff, and then your ears are clearly picking something up, but yet you're not able to see anything what's going on in here. So again, you could just Google this. I can hear it. Why can't I measure it? And get the PDF off of the Audio Express website. So let's go back to our presentation. So from the current slide. So here was the other thing that I did here was just looking at the time domain signal. So there were some little spurious, interesting things going on. I got to say, I have no idea what it is. Was not necessarily audible, but you just see it here. Noise should be a broadband and basically have a pretty stable, let's say, RMS level. So something's happening with this particular sound card where you got these little spikes. They're still extremely low. Again, this is on a digital basis. They're, on the micro full scale level. So voltage level wise, they're still low, but there's clearly something that's happening in here that's not happening in the case of an audio analyzer. So take away from this, take a look at your the time series data of the noise floor. Again, just don't take on faith some single number that looks really awesome in a spec sheet. So going back to the high order harmonic stuff. So here is, this was 0 dBFS signal that I put in to both devices. So here is the AP, and then here's the sound card. But notice, okay, so the audio precision, second harmonic, third harmonic, a few upper level harmonics. But look at more of these higher order harmonics. Again, they are very low in level, but I got to tell you from firsthand experience that there are distortion artifacts, and in the speaker side of things, audible rub and buzz, where those high order harmonics can be minus 110, minus 120. So if what your measurement device, if that's having high order harmonic distortion, in that minus 110 range, that might be actually giving you a false impression that you might be having worse high order harmonic distortion than what your device is putting out. So here was just the overall THD plus noise. This was at plus 3 dBu input. So again, a pretty significant difference, minus 90 versus about minus 107 dB. So these are again over at the 48 kilohertz range. So this is just over the audio bandwidth. So now I use the multitone signal. So this case, I had 32 simultaneous sine waves, basically at 1/3 octave center frequencies. And the crest factor in this particular multitone is about 10 dB. So it's not, let's say, quite as large as highly impulsive music, but in today's modern music, with all the compression that's happening, a lot of it's in this crest factor range, maybe even less. But the bottom line is multitone is just way more of a realistic test signal. So here is what's happening with the multitone. So here's the FFT of that. So we see in here that the noise floor is about 20 dB lower. Now, again, this is on, let's say, a per bin basis. But one of the things that multitone can show is not only what's happening with increases in noise floor, but oftentimes, not in this case, but oftentimes I've seen some weird intermodulation distortion occurring with a device when multitone is used as its excitation signal. And then, of course, you can, with the AP, it's very, very easy just to crank up the level of the multitone to see what's happening. So, this is the thing, is that you can get in and just zoomed in here. You can just see in more detail what's going on, that with the multitone, you start to see some little IMD components kind of popping up out of the noise floor here. So you see with the AP, it's basically just those tones and basically 0 to very, very little intermodulation distortion caused by those tones, but that is not so much the case with a sound card. So this is one of the things I love about multitone, regardless of what it is that you're testing, but in particular with electronics, that the multitone can often generate distortion behavior that you do not find with a sine wave excitation. And you'll see stuff like this. You'll see IMD stuff. You'll see an overall increase in noise level. And then with the multitone, once you've dialed in a particular RMS level like I did, and you do that by playing around with the phase relationships of the tones, and there's some tools in the AP software to make this easier. But once you dial that in and you say, okay, at this generator output level is X, like in this case, plus 3 dBu, then you got extremely fine control. You say, what happens if I just kick it up by half a dB? Well, you just tell the AP software, I'm going to go from plus 3 to plus 3.5. Then you have that extremely fine granularity. And what I've seen in my years in the biz is sometimes, especially with a complex signal like multitone, you kick it up just a few tenths of a dB, suddenly you got other distortion activity that's going on that you would not see otherwise. So to conclude with what's happening in here, so what's the nice thing with sound cards? Well, the prices are quite attractive. So it's very good on the pocketbook. Although the higher end sound cards, you can, even for low channel counts, they're typically going to be above $1,000. But on a cost per channel basis, they can be quite attractive. However, you got to be cognizant that they're typically going to be higher noise and distortion than an audio analyzer. If you are concerned that there might be, especially when measuring electronics, even if it's, let's say, an amp or some device that does not have much gain, if you have any concern that there might be some sort of voltage spike that comes out of this device you're testing, sound cards can be much more susceptible to damage just because the front ends are not designed to handle tens of volts, let alone 100 volts plus going in there. And then in the case of the AP designs, we have some other circuitry to act like literally like a circuit break if you suddenly hit it with a high surge of signal. There's other further protection mechanisms in place that you don't see in a sound card. Why? Because a sound card is made for recording, not for test and measurement. And there's really no need for the manufacturers to go through the engineering efforts and the cost of putting this stuff in there. If it's important for you to get calibration, I say true calibration is not possible. Now, people can get sound card based systems calibrated, but if there's anything that drifts, there's really not much that you can do. In the case of the audio precision analyzers, I mean, we have the way that the architecture is done, that in our calibration process, both on the manufacturing side and after the fact, we actually put in what we call in the instruments there, put in these calibration constants, which actually further dials in due to component variability, which is why you do like a loop back measurement of an AP, and it's like flat across a 20 to 20K to within thousandths of a dB. I mean, yes, we use extremely tight tolerance components, but we also do these other tricks of putting in these calibration constants to dial it in that much more accurately. These sorts of things are not possible with a sound card. So here's how you can reach me. Very simple email, danf@ap.com or danf@audioprecision.com. And then my phone number there with the +1. So feel free to telephone me, text me, and I'm more than happy to answer any questions you might have or further clarify stuff. So I guess I could just open up the floor for Dave and Simon for any questions, thoughts, commentary, however you guys want to proceed from here.
Thanks very much, Dan. Just one thing, just to clarify, when you're making a comparison between audio analyzers and sound cards, you're really talking about one facet of the audio analyzer. Is that right? The front end, so to speak?
Correct. Yeah, really, it's really two elements. It's the analog part of the analyzer, right? So you're bringing up a good point there, Simon, because for digital analysis, I don't want to say digital is digital, but it really is. I mean, sound cards, especially the higher end cards. If you're dealing with, say, okay, I want to use this high end recording interface to look at what's going on with the digital signal path of my device under test. That's going to work, actually work quite well. It's when you want to be getting into especially more nuanced characterization of a device in its respective analog world. That's where these differences I'm highlighting can become quite important.
Yep. And so you kind of preempted it. Once you've got to the point of digitization, do you think that there's very little difference after that? So, whatever you bring the data in by USB, I guess, to a computer and do FFTs there. Is there anything, any differences to speak of in that facet?
So are you talking about now when the signal path from the get-go is digital, or when you're talking about? No,
I'm talking about when you've passed the analog front end and you've got your data digitized, whether it's from an AP analyzer or a sound card.
Right. Yep.
Do you consider those to be pretty much the same?
Yeah, from a ones and zeros standpoint, yes. Yeah. However, it gets back to, so what's going on with that, let's say on the input side. So what's going on the A to D side with that sound card device, right? So it's like, first and foremost, okay, whose chipset are you using? As I've said before, at the beginning, you look at these cards. In fact, I got to say, us folks at AP kind of benefit from the high-end sound card market because they're buying chips in quantity that we would not be able to do, and hence that helps to cause the price of the chips to be quite attractive. It's what you do with it after the fact is another story. It's like, okay, what's the PC board layouts that we have? What's What's the grounding schemes that we put in? What do we, like, as I mentioned, the auto ranging circuitry, that additional circuitry, very low noise, very high precision circuitry to always ensure, in the case of the AP audio analyzers, that analog signal is as much as possible in the sweet spot of the converter. The sound cards don't have that. Again, why? Because they don't have to. I mean, last thing you want to do in the middle of a recording session is suddenly have the sound card auto range when the kick drum is going thump, thump, thump.
Right.
It's just not, doesn't make any sense.
Just back at the beginning of the talk, you mentioned some sound cards claim 24-bit, but they may not be. Could you elaborate a little bit on that?
Yeah. So what I've seen, and exactly. Well, first of all, there is the dithering being applied will certainly eat up a little bit of those lower bits. Now, some of the things that I've seen, and actually, I'm just am I still? Are we still sharing
share again?
here?
Yeah, you can go again if you like.
Yeah, I just want to show some of these special signals that are in the AP software for doing these types of measurements. So let's see, share the screen. I will go to this here, and this is the AP software. So actually, this is the higher end sound card that I measured. I'll get into some of the interesting measurements with that. But what I'm going to do real quickly is I'm going to go over to the sequence mode. And I'm just going to put in what we call a signal path and just choose a digital signal path so I can show you what some of our interesting signals are like. So I'm just running this in demo mode. So I'll just go good old, let's say good old speed if here, digital unbalanced, both in and let's say out. Again, I can't make any measurements because I don't have anything physically hooked up. But there are special signals that we have. And one of them, there's a couple in here. So there's this bit test signal. So the bit test signal is a pseudo-random number sequence. For those of you that might be familiar with MLS, maximum length sequence, it kind of sounds like that when you listen to it. But it's a pseudo-random sequence where you can choose in the software whether it's 16 bits or 24 bits. And what comes back for a measurement is a bit error rate, or on a percentage basis. So if you put a bit test signal and you say this is a 24-bit test signal, and I'm putting into this device, then if you get basically 0% error, then what's coming back on the digital stream is saying, okay, you're giving me 24 bits, I'm giving back to you a full 24 bits. If it's a if it's a number above that, then it's like saying, okay, what's going on here? So the other cool thing that we have, and again, since I don't have a piece of equipment hooked up here, I can't show, but we have these things called walking ones and walking zeros. And what it is, it's just like a DC pulse, you could think, that moves in amplitude. So it exercises each bit. And our display is like these little green rectangles. So if it's 24-bit, you got 24 rectangles in there, and they light up when the bits are active. Or they light up. You could do walking runs, or 1 bit is active. Walking zeros is only 1 bit is not active. All the other bits are active. So kind of a long answer to a short question. So what have I seen doing this stuff? Stuff that I've seen is with the bit error rate, with that signal, it's like, it's not 0%, it's above that. So I'm clearly not getting my 24 bits back. Then I do the walking ones thing, and it's like it gets down to bit number 22, and bits 22, 23, 24 never light up because they're never there. So these are the things that can be done. So along that end, going back to using a sound card in the digital world, and then someone getting forced with the AP software here, if they characterize their sound card interface and say, you know what, I know this thing is truly a 24-bit device, it's got super low, digital noise floor and all of that, you can now use that piece of hardware to characterize what's going on with other pieces of hardware in your studio or elsewhere with a high degree of confidence using these types of signals. So we can, so I'm done with this here. So I guess I can do what's the stop sharing.
Yeah.
Awesome.
Okay. So we found that article. Let's see here. There we are. Sorry. Yeah, so it's on the Audio Express, the article that Dan was mentioning. If people want to look it up, we'll put the link in the description below for that. And of course, people can visit the AP website. That's pretty easy to find, ap.com. You guys must have been early in your URL.
We were. Remember, nerdy engineers were aware of the internet and the value of that way before Associated Press was.
Right. Yeah. No kidding. Okay. Any more questions, Simon, that you'd like to ask?
No, that's it for me. Thanks very much, Dan.
Yeah, I know I
All
threw
right.
a lot of stuff out there, but as you can tell, I'm pretty passionate about these things, and I got a few years under my belt, as you can tell, with the gray hair. So, as I said, for your listeners out there, feel free to reach out. More than happy to engage with you to help me out, answer your questions, or for that matter, we'll provide guidance on what's the best way to make high quality and believable audio measurements.
All right. Well, on that note, that's a great summary, Dan. Thank you very much for joining us today. We really appreciate it. That's a fantastic presentation, and we can very few interruptions into your presentation, so we were just listening earnestly there. So, of course, everybody, hope you enjoyed that. Please like, subscribe, and share this. And once again, Simon, Dan, thanks for hanging out with us today.
Okay. Thanks, folks.
Thank you.
Okay. Bye-bye, everybody.